All right, we are finishing up chapter 3, exploring two variable quantitative data. Today we are looking at section 3.3, transforming to achieve linearity. It's a rough word for me to say, I guess. So some learning targets. You should, by the end of the section, be able to use transformations involving powers, root, or logarithms to create a linear model that describes the relationship between two quantitative variables and use the model to make predictions. Determine which of several transformations does a better job of describing the relationship between two quantitative variables. Now, this should be pretty familiar to you when you in like a physics or a science class when you're trying to create a line of best fit or a linear model. But it wasn't linear, so you had to make some adjustments to the data to get it to look like a line. So it's going to be a similar idea here. This is kind of a graph of a bunch of things. So the colors of each circle represent where the geographical region. The size of each circle is the population. And then obviously the x-axis is how much money they make per person, and the y-axis is the life expectancy of people there. So the relationship between life expectancy and income is not linear. And that's kind of obvious, right? You kind of see this curve coming this way. Right? So it's coming up and then it's curving. Okay. So the question is, what is that? Well, that idea here where I start low and I get, all right, a graph that kind of looks like this would be a logarithmic graph, okay, if we're familiar with that. So we can straighten things out using logarithms here. And if I actually took the log of that income, so basically every point I did log of whatever, and then that's my new x value. And then I kept my same y value. We can start to see this thing looks a lot more of a straight line now. And so applying a function such as the logarithm or square root to a quantitative variable is called transforming the data. Transforming data amounts to changing the scale of measurements that was used when the data were collected. So there's a couple different ways you can do it. One way is we looked at a logarithm. Another way is a power model. So if I had y equals a times x to the p, basically what we're going to do is we're going to transform the exploratory variable x by raising them to some power p. So every x value is now going to be raised to some power, and we're going to see if that scatter plot is linear or not. So I have this problem. Imagine that you have been put in charge of organizing a fishing tournament in which prizes will be given for the heaviest Atlantic Ocean rockfish caught. You know that many of the fish caught during the tournament will be measured and released. You are also aware that using delicate scales to try and weigh a fish that is flopping around in a moving boat will probably not yield very accurate results. It would be much easier to measure the length of the fish while on the boat, and then what you need is a way to convert the length of the fish to its weight. You contact the nearby marine research laboratory, and it provides reference data on the lengths in centimeters and weight in grams for Atlantic Ocean rockfish of several sizes. Here's a scatter plot of the data. So this is just a bunch of data they have of length and weight, and you can see, hey, it's going to be curved, okay? And now it's curved up, so the question is like, well, hey, is this a power function, an exponential, a logarithm, which one? Since it's curved up, it's going to be, well, we're going to try a couple things out. So we're going to try out with powers here. So because the transformation made the association roughly linear, so they're doing the transformation of y and x cubed. So every x value, every length is going to be cubed, and they're going to see if that turns this into more of a linear relationship. And so when they do that, when they do the x cube it gives us this equation of the least squares regression line. And they want us to define the variables you use and then kind of do an estimate of a number. So we're given the y and the x cubed, and they kind of already did the output for us here. So we just got to take this and use our skills from 3.2, kind of create the least squares regression line. So remember, I'm I'm looking at the coefficients. It's going to kind of only find my A and my B. The constant is the y-axis, the y-intercept. It has no variable on it, so that's my constant. So this 4.066 is going to be my A value. Then they're saying this is my length cubed, so that's the coefficient for the length cube or the x cube. So we actually have this formula. Weight hat, so the predicted or the um, estimated weight is equal to 4.066 plus 0.0146774 times the length cubed. And remember, look, we don't use x and y really, we use the name of the variable. What are we actually solving for here? And that's kind of how you get away with how you know how to define the variables. So now I just ask, okay, what is it if the length is 36 centimeters long? So I'm just going to take 36, plug it into here, and I get that the weight is approximately 688.9 grams. So if we then graph that and all the data points, yes, I know the scale gets a lot bigger, but look how much of a linear relationship this looks like now. All right. So that's with the power model. We turned every x and we raised it to the p. Now we could do something different. What if I didn't want to change my x's? What if I want to change my y's? Well, to get rid of this x to the p, the way I would undo that would take the p root. Right? If I took the p root to this, I'd undo the p, but I'd have to do the p root to the y. So you could also graph x comma p root of y. And since this one was linear, the same idea, it should be linear as well. Some of the data points might be a little bit different, but they should still be fairly linear, which it is. And now you notice my length is still the same, but now each weight has been cube rooted. Yeah. So the previous scatter plot shows the relationship between the length and cube root weight is roughly linear. Here is our equation now. So it's going to want us to find the equation and find that same value. So again, I'm looking for the coefficients. Those are going to give me my A and my B. And then I have a constant and a length. So in this case now, it's going to be the cubed root of weight hat, right? I'm using this variable in context, but it's the cubed root now. It's not just the weight, it's the cubed root of the weight equals the coefficient, the constant coefficient, negative 0.02204, plus the length, 0.246616 times the length. So now when I plug this value in, I get my grams. This is approximately 694.6 grams. So if you notice like, hey, this is a power function, you could either raise the values of the exploratory variable, the x to the p power, and plot those, or you could take the pth root of the values of the response variable y and plot that. So you can either do x to the p comma y or x comma p root y. So that's powers and roots. Okay, so that's one option, is either the power or the root. The other option is with logarithms. So when transforming data that is following a power model, what if you had no idea what value of p to use? A scatter plot of the logarithms of both variables should produce a linear pattern. Why? Well, for this reason, if I had y equals a times x to the p, if I logged both sides, what's going to happen? Well, if you remember if you recall your log rules from pre-calculus, if you multiply two things of a log, you actually split them up and you add the two separate logs. And then the next thing is that this log here, well, the power rule for logs is that if you have log of something to the power, you could bring that power out in front. So I have this problem. In the predicted examples, we use powers and roots to find the fish model predicted of the Atlantic Ocean rockfish from its length. We still expect a power model from the form or weight equals a times length cubed based on geometry. Here, once again, is a scatter plot of the data. So this is length and the weight. Now we log both sides of it. Okay, so log the length. Let's go back. So this is the original data, right? Original data. I can log both the x and the y, and I get more of a linear, and I see also the residuals of the logs. There's no clear pattern, so it seems like this is going to be a linear relationship. And now I can go ahead and look at the values here. Um, So question one says, based on the output, explain why it would be reasonable to use a power model to describe the relationship between weight and length for Atlantic Ocean rockfish. Well, the scatter plot of log weight versus log length has a linear form, and the residual plot also shows a fairly random scatter of points about the residuals. So a power model seems reasonable here, right? It seems like this is making a linear model, which is good. For B, it says give the equation of the least squares regression line. Be sure to define the variables. So it's important now we log both variables. So I really have log of weight equals, I'm always looking at the coefficients and then these names. So the constant is my A, negative 1.89940 plus 3.04942 times log the length. Okay. And now I want to test that same 36 centimeter long that we've been looking at. And if I plug 36 in, you might be wondering how we got all this. Well, you could just plug this straight into your calculator to get it equals to 2.846. If you want to see that, right, it would just be negative 1.89940 plus 3.04942 times log of 36. 2.846. So now I have log weight of 2.246. In order to undo that, I need to raise both sides to the 10. 10 to the log base weight, the 10 and the log undo each other. I'm left with just weight, but I would have 10 to the 2.8464, so it comes out to 702.1 grams. So now, what if x and y have a relationship that can be described by an exponential model with the form y equals a times b to the x? So a scatter plot of the logarithms for y against x should produce a roughly linear association. Why? Well, same idea. I could take the log of both sides. Again, I'm going to split them up. Boom. So I can pull that x down again. And that's how I kind of get the x out of the variable here. So it's basically looking like, regardless of if it's a power or an exponential model, I can actually just log both sides and see then, hey, is this linear or not? So Gooden Moore was one of the founders of Intel Corporations. Predicted in 1965 that the number of transistors on an integrated circuit chip would double every 18 months. This is Moore's law, one way to measure the revolution in computing. Here are data on the dates and numbers of transistors for Intel microprocessors. Here is a scatter plot that shows the growth of the number of transistors a computer chip from 1971 to 2016. Notice we use years since 1970 as the exploratory variable. We'll explain this on page whatever. So Here's a scatter plot of the natural log or base E logarithm of the numbers of transistors on a computer chip. So we kept years the same, we just logged, or we took ln this time, of the y value variable. So we can see here, hey, the scatter plot of ln of the transistors versus years since 1970 has a fairly linear pattern. So an exponential model seems reasonable here. If you looked at the data here, boom, I will now have the equation. This is from that like Minitab outlet. I now have the equation ln of the transistors equals 7.2272 plus 0.3542 years since 1970. If I wanted to use this model, I would then put in one from 1970, so in 2020 would be 50 years. So I'd plug this in. Now, in order to undo that log, right, it's going to be e raised to both sides. We'll undo the log, so the number of transistors is equal to just e raised to that power. This this model predicts that the Intel chip made in 2020 will have about 68 billion transistors. So I think this is a nice little wrap up subsection. Putting it all together, which transformation should we choose? Suppose that a scatter plot shows a curved relationship between two quantitative variables, x and y. How can we decide whether to use a power model or an exponential model better to describe the relationship? So here is some data. So how is braking distance for a car related to the amount of tread left on the tires? Researchers collect data on the braking distance measured in car lengths for a car making a panic stop in standing water, along with the tread depth of the tires in 1/132 of an inch. Here is a linear regression output of 3 different models along with a residual plot for each model. Model 1 is based on the original data, which model 2s and 3 involve transform data. So right off the bat, you can see that the residual, it shows a pattern, right? This has a pattern. So I know right at the bat that I don't want to linear, that my original data is not linear, okay? Because I see a pattern here. So that's that. Second model, I don't see as bad of a pattern, right? It seems kind of more random. And this is ln of both, ln of braking distance and ln of tread. So x and y. And then here, this is ln of braking distance versus tread depth. And again, I see kind of a pattern again. So that's not a good sign. Also, as you notice, maybe in the data, my R squared is about 0.82. For this one, it's 0.99. For this one's 0.886. Now, again, you must know if it's a linear model or not before that's useful. But it is good to see, hey, my R squared is increasing as well. So it seems like I'm getting a better model in model 2 than model 1 and 3. So first, based on the residual, since the middle data, the middle one is the most random out of all of them, there's no pattern. That's probably the best one to produce a linear model. So my x would be ln tread depth, and my y would be ln braking depth. So that seems like the most appropriate model right now. So we picked model 2. So now let's come up with our linear regression. So we're going to have ln of y hat equals, well, now at my constant 2.903 minus 0.26 times my ln of x. Right? So my ln of braking distance equals my 2.9034 is the constant coefficient. That's my a. This is the coefficient for my ln tread depth. That's my x variable. So I go to here. And so then we're going to see if I had a tread depth of 3 out of 32 inch, then my braking distance, my approximate braking distance would be 13.57. So for this problem, it says, using the model chosen part A, calculate and interpret the residual for the trial, where the tread depth was 3 out of 32 inch stopping distance. So um, you would need to be given, so in the trial, the stopping distance is 13.6. So that's the given, that's an actual value. When I did when I plugged 3 into my model, my approximated stopping distance was 13.57. So to find my residual, I do actual minus approximated, and I get 0.03 car lengths. So the way to interpret your residual is when the tread depth was 3 out of 32 inches, the car traveled 0.03 car lengths further than the distance predicted by the model using the model where x equals ln tread depth and y equals ln braking distance. So we'll talk more in class about which models to use and how do you know which ones to use. But it's always good. You kind of saw the good 3 graphs here, just a straight up one where you ln both sides, and then one where you only ln the x variable and kind of what goes from there. So we'll talk a little bit more about which model to use, but it's important to know your options here. So that is all. So the learning targets to finish up is you should be able to use transformations involving power, roots, or logarithms to create a linear model that describes the relationship between two quantitative variables and use the model to make predictions. Determine which of several transformations does a better job of describing the relationship between two quantitative variables. Right?